A very nice application for calculus is to optimize things. This is huge for businesses, for life in general. We want to make things the best that they can be, or find the minimum amount of materials we need to use, so we're often optimizing. And why is this super helpful with calculus? Well, calculus is the first thing that really made it easy on a graph to find maximums and minimums. You have your first derivative test and your second derivative test to find maximums and minimums. So first of all, we have to find a problem that needs to be optimized. We're going to look at a couple examples here. Okay? What is the smallest product? So this is what we're trying to optimize, a product. And we're trying to make it as small as possible. But you know that one number is exactly 7 greater than the other number. Okay? So it could be 1 and 8. 1 times 8 would be 8. Is that the smallest possible? Oh, I could use 0 and 7. Then my product is 0. That's even smaller. What would make it the smallest possible? And this is actually one, I think if you guessed and checked, you'd probably find the right answer pretty quickly. But how do we set this up so that we can use calculus? Okay? So we think about our situation. We have two numbers. We'll call one number x, the other number y. It doesn't matter which one is which, but for just argument's sake, we'll say x is the bigger number. Then we can write our product will be x times y. We want to write an equation with the product because the product is what we want to optimize. So we want product equals, and it's going to be x times y. But the problem right now is we have two different variables. And for graphing, all of our graphs have had a y and an x, which is just two things. Now we have a p, an x, and a y. We have three things. So we want the right-hand side of our equation only to have one variable. And because we know that x is the bigger number and it's equal to y plus 7, we could rearrange that and substitute it in. Right? Instead of writing the x, I could just replace it with y plus 7. And now I have an equation that just has product and only one variable. It's a problem. Y squared plus 7y. If I find its vertex, I'm going to find its minimum. Does it make sense that in this situation, that's the point I'm looking for. When does that happen? Well, I could complete the square like I did in grade 11, but now that I have calculus, and calculus is so much nicer, I just take my derivative. Take my derivative, I set it equal to 0. Y equals negative 7 over 2. You could even do your number line for your first derivative test. We knew it was a problem already, but it is decreasing, then increasing. So you know that when y is negative 7 over 2, you're going to get a minimum. Well, we can plug that in and get the x value too. And we find out that the smallest product you could get, if you had two numbers multiplied together, would be negative 49 over 4. So optimization problem, first of all, you want to figure out what are you trying to optimize. In this case, we wanted, and optimization will either be a maximum or a minimum. Here we wanted the smallest product, so we wanted to have an equation that was product equals. You take the information that you're given, and your goal is to get product equals with just one variable on the other side. So optimization problems often involve manipulation to get one variable. Lots of substitution, sort of like systems of equations. They give you two pieces of information, and you have to substitute one into the other. And then once you have your equation that has only one variable on the right side, then we can use our skills in derivatives to find the max or the min, take that value and plug it back into the original equation and solve. If the product of two positive numbers is 36, and the sum of the first number plus 4 times the second number is a minimum, all right, so I'm going to just take out my highlighter. What do I want a minimum of? I want a minimum sum. What are the two numbers? I'll break down what I have so far. I have one number, I'll call it x. Another number, I'll call it y. I know that the two numbers, x times y, is equal to 36. I want to optimize my sum, and I know from the question that the sum of the first number plus 4 times the second number is a minimum. So here, highlighter-wise, that's what I want to optimize. I want that to be a minimum. So I use the information of the product, and you could either, like I solved for the y, it doesn't matter. You could solve for the x or solve for the y. You'll just get the same answer in a different way. But once I've solved for the y, that lets me plug it in, and I get an equation that has only x. So the preliminary step, take everything you know, and your goal is to get an equation for the thing you want to optimize with only one variable. Then you can apply calculus. Can you do the derivative of this? Right? Would you move that x to the top? Do you like doing that, where you make the x the minus 1? Is that easier for you? Or would you like to use the quotient rule here? I think the x to the minus 1 is a little bit nicer. We do the derivative of x is 1. If you had x to the minus 1, the minus 1 would come out in front, making minus 2, so I just put that x squared on the bottom. And if we set our derivative equal to 0, we can solve. You see that I can cancel out that negative 12 because the question said two positive numbers? So now that I know that x is 12, I can tell that y is equal to 3. So what are the two numbers? The two numbers are 12 and 3. Here's our number line showing that it is a minimum. manufacturer wants to design an open box with a square base and a surface area of 108 square inches. So that's the materials they want to use, but they want to make that have as big a volume as possible. So as far as my highlighter goes, what do I want to optimize? I want to optimize volume. So I'm going to want to write an equation, volume equals. Here's our picture of the box. It's a square base, so those sides will be x. The heights can change, so its height would be h. Write out what we know. Okay? How do you figure out surface area? Surface area is adding up all the sides. The bottom would be x squared. The four sides are all x times h. There's an open top, so it wouldn't have a surface area on the top. Does that make sense? So your surface area is going to be x squared plus 4xh. Your volume is x times h. So right now, we can't optimize yet because on the right-hand side I have two variables. So I look at my first equation. Could I get the h or the x by itself? What would be easier? Because you know the surface area needs to be 108. Think it's easier to get the x or the h? The h. So I would have to move the x squared over, divide by 4x, get the h by itself. And once I have that h by itself, that allows me to plug it in to the other equation. And once it's plugged in, we've done our setup. Now we can optimize. We want that volume to be as big as possible. So we take the derivative. This is like curve sketching. We're trying to find maximums and minimums. But in this one, we want to find the maximum. So I take my derivative, set it equal to 0, and solve. And -6 just doesn't make sense in the situation of the question. Do you understand that you can't have a base length of -6? If you had done your number line and included the -6, first of all, do you see your volume equation? There's an x cubed equation. Its leading coefficient in front of that x cubed is negative, so it's going to be going down as you go from left to right. Makes sense that it would have this kind of shape. The -6 is actually a minimum or a local minimum on the graph, but we wanted to find when the volume was a maximum, so then our dimensions will be 6, 6, and 3. really like this problem, if I was fiddling with this problem, I would probably change this number. I'm not going to because all my notes would be wrong. I'd change it to 355 centimeters cubed. And the reason I change it to 355 centimeters cubed, because that is exactly what a can is. A can is 355 milliliters. Did you know that 1 centimeter cubed is exactly 1 milliliter of water? So, this is a huge, important question. Because if you are a soda pop seller, Coca-Cola, Pepsi, you're selling 355 mils in that can. You want to minimize how much aluminum you use. Because that's an expense to you. If you can make it less, you're going to save money. Okay? If you can find a way that Coca-Cola, either on a bottle or on a can, could save 0.5 cents a can, you'd be a millionaire. Because they produce so much, right? If you can find that small little thing to make it that much cheaper, because they have such a big product, you're going to save them millions and millions of dollars. You'd be like, you can pay me $500,000 a year. Thank you very much. All I did was take off a little bit of aluminum off of their can. Okay? So this question is basically that question of, we want it to fill up a certain amount. What shape should it be? Did you know that if you wanted the shape that maximizes volume and minimizes surface area, do you know what shape that is? Close. Hexagon is close. It's a perfect sphere. You have a perfect sphere, it uses the least amount of surface area to hold in it. The only problem is if you sold Coke in spheres, people like to put the can down. It's going to roll all over the place. Probably not make them very happy. So there's just, sometimes we also have to think about practicality, and they affect maximums and minimums. So there's lots of variables involved. But if you can find something that saves a little bit of money, right, that can be a good thing. In my first year, well, before I'll tell you a story. Before, because like second year of university, I got a summer job at a water company where we sold, special filtered water. And part of our job was that the filtration machine, we'd fill up bottles, and we'd put bottles into cardboard boxes, and the cardboard boxes would go off to the stores. And I started loading up a box, and I put in 12 bottles into the box, and they're like, oh, no, we only put in 10. And I was like, why? The box, if you offset them a little bit, I can fit 12. No, we've always done 10. It's my first day of work, okay? So I'm like, So later in the day, I ran into the boss and I said, why do we only put 10 in? He says, well, only 10 fit. I said, no, if you put the bottles so that they're interlocking a little bit, we could fit 12 in this box. He's like, really? That'll save us. We can ship more in less space. We can store more in less space. This is great for our business. It's not going to be hard to tell whoever buys water from us, we sell it in packs of 12 now instead of packs of 10. And this is going to be better. He said, you get a raise on your first day. I was like, that's wonderful, but you haven't told me how much you're paying me yet. So I don't know if I actually got a raise on my first day or not, because I was hired and I never found out what my actual wage was. But supposedly, I got a raise on my first day. And after that, the company always put 12 in the box, because it was the maximum that they could fit, and it made more sense. So if we can solve those things, it can save companies money. So again, what do we know? And what do we want to find? And what do we want to optimize? We want to What do we want that's a minimum? Minimum material. Can you see that that minimum material would be a minimum surface area? Do you remember all of your formulas? Surface area of a can, would you have figured this out? Here's the visual, so you never have to memorize the formula. Well, you have to still memorize it. Let's pretend this is a perfect cylinder. Close the lid so I don't spill water. The bottom is a circle. If it was a perfect cylinder, the top would also be a circle. In the formula, you have 2 pi r squared. Do you see that those are your 2 circles? And then, if you don't believe me, go home, go into your pantry, every single tin can you have, pull off the label and see what shape it is. Because if you have a label on a tin can and you pull it off, it makes a perfect rectangle. It also makes it very fun for your parents who now have a whole bunch of cans in their pantries without labels. Right? Practical joke you can play on. Oh, I'm going to get in trouble. Yep. Just like take off the labels and switch. Then they think they're making something for supper. Right? They're like, I'm going to make something with black beans. It's canned pineapple. Big surprise. Anyways. This rectangle that you pull off, can you see that the height of the rectangle is the height of the cylinder? And the length of the rectangle is all the way around that circle, which is your circumference. In your formula here, 2 pi r, there's your circumference, times your height. That's this rectangle. So add the 2 circles and add this rectangle, and you have your surface area. It's important to come up with ways to remember formulas that make sense to you, because you don't get a formula sheet. Then you have to know all the formulas. So the better ways that you can remember, the better it is. Okay, what else do we know? We know the volume is 512. That volume is pi r squared times the height. And we could get the height by itself. Because right now we've got r and h in our surface area formula. We want to substitute in, so we get a formula that just has one variable. And now I have a surface area formula just with r. And now that we have that, now the calculus comes in, we can do our derivative of our surface area. Right, I would think of that r as r to the minus 1. If I was showing my work, I probably would even I'd probably write that out like that. Just visually it makes sense for me. I have the answer here, so I jumped to that, but I probably would show, if I'm doing my own work, just makes it make sense along the way a little bit better. That r is an r to the minus 1. The minus 1 comes out in front, subtract 1 from the exponent, and set that equal to 0. And we get r cubed is 1,024 over 4 pi. Which is 4.335. which makes the height almost, I think, perfectly double.
What did you do during the steps where you made the derivative of the surface area equal to 0 from
here to here?
You took out the r squared on the bottom of 1024, and then you got r cubed.
So if I don't like that fraction, opposite of dividing, multiply. And if I multiply everything by that r, that makes this get an r cubed. When I distribute, cancels out that r squared there. Still gets a 0 here because times in by 0. But it makes things a little bit easier if we don't have that on the bottom. Yeah, good question. Yeah, anytime if there's a place where you're like, how do we go from there to there? Definitely ask that. And we get 4.335. Was there units in the original one? Yes. So it's inches. So yes, we should include units. Does this bring back memories of grade 11? This is a grade 11 pre-calc question. Remember the fencing questions to make the maximum area? And now we have calculus and we can do it so much easier. It's a crazy thing. You learn more complicated math and it makes previous math easier to do. But in order to do it easier, you have to learn a whole bunch of complicated stuff along the way. But so let's remember a little bit of what we would have done in grade 11. Again, you would figure out you want a maximum. What do we want a maximum of? A maximum area. So that's the equation we want to make, an area equals equation. Well, what do we know? Area is going to be those two x's times the y. And all of that's getting fenced, so 4x's plus 3y's is equal to 200. Because there's 200 feet of fence. We need to get one of these variables by itself. I decided to get the y by itself by moving the 4x over and dividing everything by 3 and substituting this in. Oh, my grade 11s would be mad at me if I gave them this too many fractions. Then if you distribute the 2x, you get negative 8/3 x squared plus 400x over 3. And if this was in grade 11, you would have to use your skills at completing the square with all of those fractions. Ugh. Anybody have a friend or a sibling in grade 11 right now? Are you doing some tutoring on the side? Now, when you tutor, you'll be like, oh, I know a way better way to do this. What's the better way? Well, we can take the derivative. It's actually a really easy derivative to do. Set it equal to 0. And solve an x is actually a really nice number. It's 25, which we can therefore solve for y, or the width, which will be 33.3. So who knows, maybe one of you decides, enough with all of this calculus and math, I just want to be a sheep farmer. And you've only got so much fence to use, and you want your sheep to have the most grass possible to eat. So then you design your fences accordingly. But that's not usually what happens. What happens on a farm is you own a certain amount of land. You're not going to not let them eat all of the land, so you put a fence around the whole thing so that they can eat as much grass as possible. Well, I grew up on a farm. I grew up on a farm with cows and fences. And I remember this one time, we got a new field that had some fence on it. And my dad wanted my brother and I to check how the fence was, how the wires were. And it was pretty sketchy, like the wires were not very good. And it was almost like a trap. So what happened is we were following this fence, and it started, the wire was nailed to fence posts. And then the fence got close to like a forest, and then the wires started to get nailed to trees instead of nailed to fence posts, because the person was like, oh, I could save some money if I just nail the wires. So we kept following the wire into the forest, and eventually the wire just went into the ground and disappeared. And then, had we been smart young fellows, my brother and I would have said, oh, we should just turn around and go out the way we came in, following the wire. But we decided it must be shorter if we just head in this direction. And we got lost in that forest for just before the sun went down, we got our way out. So it was good. A rectangle is formed in quadrant 1 with one corner at the origin and the other on the line y equals 8 minus 2x. We want to maximize the area. So it's a little less straightforward as far as visualizing it right from the beginning. Alright, well, we want a maximum area. It will be length times width, x times y. We draw a picture of this. We have negative slope, y-intercept of 8. One corner is at the origin, the other corner is on there. And can you see that as you make that other corner in different places, you get different areas of that green rectangle. But since we know that that line is 8 minus 2x, I mean, you could think of this point, instead of x comma y, you could replace the y with an 8 minus 2x. Oops, that's what I wanted to do. And then we have an area in terms of one variable. So I think with the optimization problems, the calculus is actually the easy part. This preliminary is where all of your work goes into. Can you get that single equation? Because once you have that equation, finding its derivative is not that hard. Setting the derivative equal to 0 is not that hard. And then you can find your solution. So try the next one on your own. I'll put the answer up in a second. I'll put up the answers, see how you did.